In this problem, we're asked to find the line currents and the power absorbed by the delta connected load. So if we note, look at our circuit, we see that we have two loads. This one is Y connected. This one is a delta connection, and we have a delta connected source, and we have line impedance. And if we look and note that this is a balanced circuit, in the delta, each leg of the delta has the same impedance. Same is true for this load, and the line impedance is the same in each phase. Okay, so since it's a balanced circuit, we're going to be able to use our problem-solving strategy entitled three-phase balanced AC power circuits. And the first step there is to go ahead and convert everything over to a Y. So we'll have a Y, two Ys, and so let's start off and let's take our source. So it's a delta connected source, and if we look, VAB is equal to 480 at an angle of 0. And again, if we look, BC lags AB by 120, so it's ABC phase sequence. So then VAN is 480 divided by the square root of 3 at an angle of minus 30 degrees. The phase voltage lags the line voltage by 30 degrees for ABC. So VAN then is 277 at an angle of minus 30. So we've got an equivalent Y connected source. We're going to draw the A phase circuit, and then if we note, we need to convert this load to a Y, and the way we'll do that is ZY is equal to 1/3 Z delta. So we have 1/3 times 30 minus J12 is 10 minus J4. So now that's converted that delta load to an equivalent Y. And now we can draw our per phase circuit. I'll show the line current for the A phase on that circuit. And now we can proceed to calculate that. For instance, if we note our two loads are in parallel, so we can combine them to form an equivalent load. Since they're in parallel, we have 1 over Z equivalent is 1 over 15 plus J8 plus 1 over 10 minus J4, and that's 7.22 minus J.36 ohms. So then our current is 277 at an angle of minus 30 divided by 0.5 plus J1 plus 7.22 minus J.36, and that gives us 35.76 at an angle of minus 34.74 degrees amps RMS. So now we have the line current, and it's very easy, for instance, now to calculate the line current in the B phase, because it'll have the same magnitude. It'll just lag this one by 120 degrees, so its angle will be minus 154.74. And then the line current in the C phase, since it's balanced system, we'll have 35.76. It'll lead this one by 120, so it'll be 85.26 degrees amps RMS. So there are the line currents. Okay, now we still need to calculate the power absorbed by the delta connected load, and I'm going to define this current, I'll call it IY2, and now we need to go through and calculate IY2. Well, we really can do it with current division because we got the line current entering, and it divides between those two loads. So IY2 is a 35.76 and an angle of minus 34.74. And if we're going to do a current divider, we want the current through this one, so we're going to put this one in the top. So we have 15 plus J8 over 10 minus J4 plus 15 plus J8. That gives us 24 and an angle of minus 15.77 degrees amps RMS. Now, that's the line current for the second load, but our load is delta connected. So what we need is the phase current magnitude for the delta connected load. And if we remember, we take the magnitude of the line current for the delta load divided by the square root of 3, we get the magnitude of the phase current for the delta load. So that's 13.86 amps RMS. So now the complex power absorbed by our delta connected load then is 3. Okay, 3 because I've got 3 phases, I'm only analyzing one. And then we have 13.86 squared times 30 minus J12. That gives us 17.29 minus J6.92 kVA.